The ground beneath our feet feels permanent, solid, unchanging in any meaningful human timescale. Yet this impression of stability masks one of the most profound discoveries in the history of science, a discovery that took centuries to develop and that fundamentally altered humanity's understanding of how the planet operates as a dynamic system. The recognition that Earth's outer shell consists of discrete plates that move, interact, and reshape the surface of the world represents not merely a scientific breakthrough, but a complete reconceptualization of geological time, planetary mechanics, and the interconnection of phenomena that previously appeared unrelated. To understand how this knowledge emerged and what it reveals about the planet requires examining not only the evidence itself, but the intellectual, institutional, and technological conditions that made its discovery possible, as well as the resistance it encountered from established scientific frameworks and the gradual, often contentious process through which it achieved acceptance. The story of plate tectonics cannot be separated from the broader history of how humans have attempted to explain the configuration of continents and oceans, the distribution of mountains and basins, the occurrence of earthquakes and volcanic eruptions, and the strange patterns observable in fossil records and geological formations across widely separated landmasses. Long before any coherent theory existed, observers noted peculiarities that would later prove significant, including the apparent fit between the coastlines of Africa and South America, a correspondence so striking that it prompted speculation as early as the late 16th and early 17th centuries. Abraham Ortelius, the Flemish cartographer who created what many consider the first modern atlas in 1570, remarked on this coastal similarity and suggested that the Americas had been torn away from Europe and Africa by earthquakes and floods, an observation that contained a kernel of truth despite being embedded in a framework of catastrophist thinking that bore little resemblance to modern understanding. This observation was repeated and elaborated by others over subsequent centuries, including the naturalist Alexander von Humboldt, who in the early 19th century noted not only the geometric correspondence of the coastlines, but also similarities in rock formations and geological structures on opposite sides of the Atlantic. The intellectual climate of 19th century geology, however, was dominated by other concerns and other theoretical frameworks that made serious consideration of continental mobility extremely difficult. The prevailing understanding held that the Earth was gradually cooling from an originally molten state, contracting as it cooled much like an apple drying and wrinkling, and that this contraction explained the folding and faulting observed in mountain ranges and other geological structures. This contractionist hypothesis, associated particularly with the work of James Dwight Dana and Edward Suess, provided a seemingly coherent explanation for observed phenomena without requiring the seemingly impossible notion that entire continents could move horizontally across the surface of the planet. The concept of permanent ocean basins and fixed continents was deeply embedded in geological thinking, supported by what appeared to be the obvious solidity and immobility of a rock, and challenging this assumption required evidence so compelling that it could overcome both intuition and established theoretical commitments. Alfred Wegener, the German meteorologist and polar explorer who had become most closely associated with the hypothesis of continental drift, was not the first to propose that continents had moved, but he was the first to compile a comprehensive multidisciplinary body of evidence in support of this claim and to present it as a serious scientific hypothesis demanding consideration. Wegener's background was unusual for someone proposing a major geological theory, as his training was in astronomy and meteorology rather than geology, and his professional work focused on atmospheric phenomena and polar research. This outsider status proved both advantageous and disadvantageous, allowing him to approach the question without the theoretical commitments that constrained many geologists, but also rendering his work suspect to those who viewed geology as requiring specialized training and experience with rocks and field observation. Wegener first presented his ideas in 1912 and published them more fully in 1915 in his book Die Entstehung der Kontinente und Ozeane, which translates to The Origin of Continents and Oceans, a work that would go through multiple editions and translations while generating intense controversy that persisted for decades after his death. The evidence Wegener compiled drew from multiple scientific disciplines and included the geometric fit of continental coastlines, the distribution of fossil organisms, the correspondence of geological structures across ocean basins, and paleoclimatic indicators suggesting that regions now at very different latitudes had once shared similar climates. The fossil evidence proved particularly compelling, as it showed that identical species of ancient plants and animals had lived on continents now separated by thousands of kilometres of deep ocean, species that could not plausibly have crossed such barriers by any known means. The Mesosaurus, a small freshwater reptile from the Permian period, had been found in both South America and Southern Africa, and nowhere else. A distribution that made perfect sense if these land masses had once been joined but seemed inexplicable under the assumption of fixed continents. Similar patterns appeared in the distribution of the seed fern Glossopteris, found across South America, Africa, India, Antarctica and Australia in Permian Age rocks, again suggesting a former connection that no longer existed. The geological evidence included the alignment of distinctive rock formations and mountain ranges that appeared to continue from one continent to another when the coastlines were fitted together, such as the Appalachian Mountains of North America and the Caledonian Mountains of Scotland and Scandinavia, or the matching geological sequences in Brazil and West Africa. Wegener also pointed to paleoclimatic evidence, arguing that the distribution of ancient glacial deposits, coal seams, and other climate-sensitive indicators made sense only if the continents had occupied different positions relative to the poles in the geological past. Glacial deposits of Permian age had been found in South America, Africa, India, and Australia, all regions that currently have tropical or subtropical climates, while coal deposits indicating lush tropical vegetation of similar age occurred in regions that now experience severe winters. The hypothesis of continental drift could explain these patterns by placing all these southern hemisphere land masses near the South Pole during the Permian period, grouped together in a supercontinent Wegener called Gondwanaland, which subsequently fragmented and dispersed. This reconstruction also explained the existence of glacial striations, the scratches and grooves left by moving ice, which pointed in directions that made no sense given current continental positions, but aligned coherently if the continents were reassembled. Despite the quantity and variety of evidence Wegener presented, his hypothesis encountered immediate and sustained criticism, particularly from geologists in Europe and North America, who found his mechanism for continental movement entirely inadequate. Wegener proposed that continents move through oceanic crust, much as ships move through water, driven by tidal forces and the centrifugal effects of Earth's rotation, but calculations by physicists such as Harold Jeffreys demonstrated that these forces were far too weak to push continents through solid rock. The absence of a plausible mechanism proved fatal to the acceptance of continental drift in many scientific circles, as it seemed to require either the wholesale abandonment of known physics or the acceptance of forces that simply did not exist at the magnitudes required. The criticism was often harsh and personal, with some geologists dismissing Wegener as an amateur who did not understand the discipline he was attempting to revolutionize, and the rejection of continental drift became something of an orthodoxy in English-speaking geology by the 1930s and 1940s. Rollin Chamberlain of the University of Chicago characterized Wegener's method as selecting only evidence that supported his hypothesis while ignoring contradictions, a charge that, while containing some validity regarding specific details, failed to grapple with the overall pattern of evidence that required explanation. Wegener's death in 1930 during an expedition to Greenland meant he did not live to see the eventual vindication of his fundamental insight, though the process by which this vindication occurred followed paths he could not have anticipated and required technologies and research programs that did not exist during his lifetime. The transformation of continental drift from a rejected hypothesis to a central component of accepted geological theory happened not through a gradual accumulation of more evidence of the same types Wegener had compiled, but through entirely new lines of investigation that emerged from geophysical research, particularly research focused on the ocean floor and on the magnetic properties of rocks. This transformation occurred primarily in the 1950s and 1960s and involved researchers who initially had no particular commitment to continental drift, and who were investigating questions about ocean floor topography, heat flow, and paleomagnetism for reasons unconnected to the drift controversy. The study of the ocean floor accelerated dramatically after World War II, driven initially by military interests in submarine warfare and anti-submarine detection, but producing scientific discoveries of fundamental importance. The development of sonar and echo-sounding technology allowed researchers to map the topography of the ocean floor in unprecedented detail, revealing features that had been entirely unknown and that proved crucial to understanding how the Earth's surface operates. The mid-ocean ridge system emerged from these surveys as a global network of underwater mountain ranges extending through all the major ocean basins, a continuous feature some 65,000 kilometers long that represented the longest mountain chain on Earth, yet had been entirely invisible until the advent of systematic ocean floor mapping. The Mid-Atlantic Ridge was mapped in increasing detail through the 1950s, revealing not only its considerable height above the surrounding ocean floor, but also the presence of a deep rift valley running along its crest, a feature suggesting extension and separation rather than compression. Bruce Heason and Marie Tharp at Columbia University's Lamont Geological Observatory produced detailed maps of the ocean floor that revealed these features with striking clarity, and Tharp in particular recognized the significance of the central rift valley, suggesting it indicated that the ocean floor was spreading apart along the ridge axis. Simultaneously, researchers studying the magnetic properties of rocks made discoveries that would prove essential to understanding both the history of the continents and the mechanisms of their movement. Paleomagnetism, the study of ancient magnetic fields preserved in rocks, had revealed that many rocks appeared to have been magnetized in directions quite different from the current magnetic field, directions that could be explained either by movement of the magnetic poles or by movement of the continents relative to a relatively fixed pole position. By the late 1950s, paleomagnetic researchers in Britain, including Keith Runcorn and his colleagues, had accumulated sufficient data to suggest that the continents had indeed moved relative to one another, as the apparent polar wander paths traced by European and North American rocks diverged into the past in ways that could be reconciled only by assuming the continents had been closer together in earlier geological periods. This paleomagnetic evidence provided new support for continental mobility that was independent of the biogeographical and geological evidence Wegener had compiled, and that came from a completely different methodology and research tradition. The decisive synthesis that transformed these various lines of evidence into a coherent theory came through the work of several researchers in the late 1950s and early 1960s, particularly Harry Hess of Princeton University and Robert Dietz, who independently proposed the concept of seafloor spreading. Hess, who had commanded an attack transport during World War II and used its echo sounder to collect data on the Pacific Ocean floor during military operations, proposed in 1962 that the mid-ocean ridges were sites where hot material from the Earth's interior rose toward the surface, creating new oceanic crust that then moved away from the ridge axis in both directions. This process, which Hess initially described modestly as an essay in geopoetry, to acknowledge its speculative nature, provided a mechanism for continental movement that avoided the impossible physics of continents ploughing through oceanic crust. In the seafloor spreading model, continents did not move through oceanic crust, but rather moved with it, carried along as passive passengers on a conveying belt of oceanic lithosphere created at ridges and destroyed elsewhere. The destruction of oceanic lithosphere was proposed to occur at deep ocean trenches, the arcuate depressions that parallel many continental margins and island arc systems, where the ocean floor was thought to descend back into the mantle in a process later termed subduction. The trenches represented the complement to the ridges, sinks where material returned to the interior to balance the creation of new material at the spreading centres, and this recognition began to define the boundaries of what would eventually be understood as lithospheric plates. The pattern of heat flow measurements supported this model, with higher than average heat flow observed near the mid-ocean ridges, where hot material approached the surface, and lower than average heat flow near the trenches where cold oceanic lithosphere descended into the warmer interior. Earthquake distributions also aligned with this framework, with seismic activity concentrated along the ridges, the trenches, and connecting fault systems rather than distributed randomly across the ocean floor, suggesting that these features defined the boundaries of distinct crustal blocks. The clinching evidence for seafloor spreading came from the study of magnetic anomalies on the ocean floor, patterns of alternating stronger and weaker magnetic intensity that formed stripes parallel to the mid-ocean ridges. Frederick Vine and Drummond Matthews of Cambridge University proposed in 1963 that these stripes resulted from periodic reversals of Earth's magnetic field, a phenomenon that had been documented through studies of volcanic rocks on land. As new oceanic crust formed at the ridge axis, it acquired the magnetic polarity of the ambient field at the time of its formation, preserving this polarity as it moved away from the ridge and was replaced by newer crust. Reversals of the field produced alternating stripes of normal and reversed polarity, and the symmetry of these patterns about the ridge axis provided compelling evidence that new crust was indeed being created at the ridges and spreading in both directions. The magnetic stripes also allowed calculation of spreading rates by correlating the reversal pattern with independently dated reversal sequences from continental volcanic rocks, revealing that different ocean ridges spread at different rates, but that the process operated continuously over geological time. The integration of these various observations into a comprehensive theory of plate tectonics occurred through a series of papers published in the mid to late 1960s by several groups of researchers working somewhat independently, but building on each other's ideas. Jason Morgan of Princeton proposed in 1968 that the Earth's surface could be divided into about a dozen major rigid plates that move relative to one another, with earthquakes, volcanic activity, and other geological phenomena concentrated at plate boundaries. Dan Mackenzie of Cambridge and Robert Parker at Scripps Institution of Oceanography developed mathematical frameworks for analysing plate motions on a spherical surface, demonstrating that the movements of rigid plates on a sphere could be described by rotations about specific poles. Xavier Le Pichon applied these methods to determine the relative motions of 6 major plates, producing a kinematic description of global plate movements that explained the observed patterns of seismicity and tectonism. The synthesis that emerged from this work constituted what Thomas Kuhn might recognise as a scientific revolution, a fundamental reconceptualization of how the Earth operates that replaced earlier frameworks with a new paradigm of comparable explanatory scope, but far greater precision and predictive power. The acceptance of plate tectonics among the geological community occurred with remarkable rapidity once the critical evidence had been assembled, in marked contrast to the decades of rejection that continental drift had experienced. Several factors contributed to this rapid acceptance, including the quantitative precision of the seafloor spreading evidence, the involvement of physicists and geophysicists whose methodological standards differed from those of traditional geology, and a generational shift in the discipline that brought younger researchers less committed to previous frameworks into positions of influence. The theory also proved remarkably productive in explaining phenomena that had previously seemed unrelated, from the distribution of earthquakes and volcanoes to the origin of mountain ranges, from the configuration of ancient climate zones to the evolutionary history of organisms on different continents. This explanatory unification represented precisely the kind of theoretical achievement that sciences aspire to, demonstrating connections between disparate observations that increased understanding across multiple domains simultaneously. The mechanisms underlying plate tectonics have become increasingly well understood in the decades since the initial recognition that plates exist and move, though significant questions remain about the details of how the system operates and how it has changed over geological time. The driving forces for plate motion involve density differences in the mantle that create convective circulation, with hot material rising and cool material sinking in patterns that interact with the surface plates in complex ways. The sinking of cold, dense oceanic lithosphere at subduction zones appears to provide much of the motive force for plate motion, with the descending slab pulling the attached plate along behind it in a process termed slab pull. Ridge push also contributes, as the elevated ridge stands higher than the surrounding ocean floor, and the newly formed lithosphere slides downhill away from the ridge axis under gravitational influence. The relative contributions of these forces and the nature of the coupling between the surface plates and the underlying mantle convection remain subjects of ongoing research and debate. The structure of the Earth relevant to plate tectonics involves a distinction between layers defined by composition and layers defined by mechanical properties, and understanding this distinction proves essential to grasping how plates work. Compositionally, The Earth consists of a metallic core, a rocky mantle, and a thin outer crust. But mechanically, the significant boundary is not between crust and mantle, but rather between the lithosphere and the asthenosphere. The lithosphere comprises the crust and the uppermost portion of the mantle, behaving as a rigid or semi-rigid unit that can transmit stress over long distances and that constitutes the plates themselves. The asthenosphere, lying beneath the lithosphere, consists of mantle rock that behaves as a viscous fluid over geological timescales, flowing slowly in response to temperature and pressure differences. This rheological boundary, not the compositional boundary between crust and mantle, defines the base of the plates and allows them to move relative to the underlying material. The thickness of the lithosphere varies considerably depending on its age and history, with oceanic lithosphere ranging from essentially zero thickness at mid-ocean ridges, where it is just being created, to approximately 100 kilometers or more for the oldest oceanic lithosphere, and with continental lithosphere extending to depths of 150 to 250 kilometers, or even deeper beneath ancient cratonic cores. This variation in thickness has important consequences for how different plates behave, with thin, young oceanic lithosphere being more flexible and easier to deform than thick, old continental lithosphere. The continental lithosphere also differs from oceanic lithosphere in being less dense, which explains why continents are not subducted when they arrive at convergent plate boundaries, but instead collide and deform, creating mountain belts and complex geological structures rather than disappearing into the mantle. Plate boundaries come in three fundamental types, defined by the relative motion of the adjacent plates, and each type produces characteristic geological features and phenomena. Divergent boundaries occur where plates move apart, exemplified by mid-ocean ridges where new oceanic lithosphere forms, and by continental rift systems where continents begin to split apart. Convergent boundaries occur where plates move toward each other, resulting in subduction when oceanic lithosphere descends beneath another plate, or in collision when two masses of continental lithosphere meet. Transform boundaries occur where plates slide horizontally past each other without significant creation or destruction of lithosphere, such as the San Andreas Fault System in California. Each boundary type produces distinctive patterns of seismicity, volcanism, and topography that can be used to identify and characterize boundaries in the modern world and to reconstruct the positions of ancient boundaries from the geological record. Divergent boundaries at mid-ocean ridges represent the sites where new oceanic lithosphere is continuously created through volcanic processes, with magma rising from the partially molten asthenosphere to fill the gap left as plates move apart. The volcanic activity at ridges is characterized by the eruption of basaltic lava, which represents the composition that results from partial melting of the mantle, and the ridges stand elevated above the surrounding ocean floor because the newly formed lithosphere is hot and therefore less dense. As the lithosphere moves away from the ridge and ages, it cools and contracts, subsiding to greater depths and accumulating sediment on its surface. The variation in depth with age follows a predictable relationship, with ocean floor depth increasing approximately as the square root of age, a pattern that has been confirmed by measurements across all the major ocean basins, and that provides a powerful tool for determining the ages of ocean floor regions from their depths alone. The spreading rates at different ridges vary considerably, from about 1 centimeter per year half rate at slow spreading ridges like the Mid-Atlantic Ridge to more than 7 centimeters per year at fast spreading ridges like the East Pacific Rise. These different spreading rates produce different ridge morphologies, with slow spreading ridges characterized by prominent rift valleys, rough topography, and intermittent volcanism, while fast spreading ridges display smoother profiles, lower relief, and more continuous volcanic activity. The differences result from the relationship between magma supply rate and spreading rate, with slow spreading ridges experiencing episodic rather than continuous volcanism and cooling between magmatic events that allows faulting and extension to create the characteristic rift valley topography. The study of mid-ocean ridge processes has been greatly advanced by direct observation using submersibles and remotely operated vehicles, revealing active volcanic features, hydrothermal venting systems that support unique biological communities, and the detailed structure of newly formed ocean crust. Continental rift systems represent divergent boundaries at earlier stages of development, Before continental lithosphere has completely separated and oceanic lithosphere has begun to form between the fragments, the East African Rift System exemplifies this stage of development, where the African plate is splitting into the Nubian plate to the west and the Somali plate to the east, along a complex zone of faulting, volcanism, and topographic disruption. The process of continental rifting involves the stretching and thinning of continental lithosphere, with normal faulting creating rift valleys bounded by uplifted rift flanks, and with volcanism occurring as the lithosphere thins and allows access for mantle-derived magmas. The magmatism associated with continental rifting often differs from that at mid-ocean ridges, reflecting the involvement of continental crust in the melting process and the potentially different composition of the underlying mantle. The transition from continental rifting to seafloor spreading represents a critical threshold in the development of new ocean basins, with the Red Sea representing a more advanced stage where oceanic crust has begun to form in the central parts of what was formerly a continental rift. Convergent boundaries where oceanic lithosphere subducts beneath another plate produce some of the most dramatic geological phenomena on Earth, including deep ocean trenches, volcanic arc systems, and the largest earthquakes yet recorded. The subduction process involves the descent of cold, dense oceanic lithosphere into the mantle, at angles that vary from quite shallow to nearly vertical, depending on factors including the age and therefore density of the subducting slab, the rate of convergence, and the nature of the overriding plate. The trenches that mark subduction zone locations represent the deepest features on Earth's surface, with the Mariana Trench reaching depths exceeding 10 to 900 meters below sea level. The descending slab carries with it not only oceanic crust and underlying mantle lithosphere, but also water incorporated into hydrous minerals formed through interaction with seawater, and the release of this water at depth triggers melting in the overlying mantle wedge that produces the volcanic arcs characteristic of subduction zones. The volcanic arcs formed above subduction zones differ from mid-ocean ridge volcanism in their magma compositions and their eruptive styles, reflecting the different conditions under which the magmas are generated and the pathways through which they reach the surface. The involvement of water in the melting process at subduction zones produces magmas that are typically more silica-rich and more viscous than the basalts erupted at ridges, and these properties lead to more explosive eruptive behaviour that poses significant hazards for populations living near subduction zone volcanoes. The Pacific Ring of Fire, which encompasses the margins of the Pacific Plate and includes the volcanic arcs of the Andes, the Cascades, the Aleutians, the Kurils, Japan, the Philippines and Indonesia, contains the majority of the world's active volcanoes and experiences the majority of the world's earthquakes, reflecting the concentration of subduction zones around the Pacific Basin. The seismicity associated with subduction zones extends to much greater depths than earthquakes at other plate boundary types, with earthquakes occurring along the descending slab to depths of nearly 700 kilometers. These deep earthquakes trace the geometry of the slab within the mantle and define what are called Wadati-Benioff zones, after the seismologists who first recognized their significance. The existence of earthquakes at such depths initially posed a puzzle, as rock at these temperatures and pressures was expected to deform by slow plastic flow rather than brittle fracture. But researchers suggested that the earthquakes may result from mineral phase transitions in the descending slab or from dehydration reactions that release fluids and reduce effective stress on fault surfaces. The deepest earthquakes are associated with the oldest and coldest subducting slabs, which maintain their mechanical integrity to greater depth than younger, warmer slabs that assimilate into the surrounding mantle at shallower levels. Convergent boundaries where two masses of continental lithosphere collide produce a different style of deformation than subduction zones, as the low density of continental material prevents it from sinking into the mantle. Continental collision instead results in the intense deformation, thickening and uplift of the colliding margins, creating the highest mountain ranges on Earth and producing complex geological structures that record the history of convergence. The Himalayan mountain belt represents the premier modern example of continental collision, formed by the collision of the Indian subcontinent with Eurasia that began approximately 50 million years ago and continues today. The collision has doubled the thickness of the crust beneath the Tibetan Plateau, created the highest peaks on Earth, and produced a zone of deformation extending thousands of kilometers into the continental interiors on both sides of the suture zone. The Alps, the Urals, and the Appalachians represent earlier examples of continental collision, their current topography and structure reflecting both the original collisional deformation and subsequent modification by erosion and other processes. Transform boundaries represent the third fundamental type of plate boundary, where plates slide horizontally past each other along strike-slip fault systems without significant creation or destruction of lithosphere. The San Andreas Fault in California exemplifies a continental transform boundary, where the Pacific Plate moves northwestward relative to the North American Plate at rates averaging approximately 5 centimeters per year. Transform boundaries also occur in oceanic settings, where they offset segments of mid-ocean ridges and accommodate differences in spreading direction, or rate between adjacent ridge segments. The earthquakes on transform boundaries are typically confined to shallow depths, where rocks behave brittly, and the deformation is concentrated in relatively narrow zones, compared to the broader zones of distributed deformation at convergent boundaries. The cumulative offset on major transform faults can be enormous, with the San Andreas Fault having accommodated several hundred kilometers of displacement since its formation, and continuing to accumulate slip that will eventually be released in future earthquakes. The recognition that plate boundaries are not fixed, features but evolve over time, represents an important aspect of plate tectonic theory, with boundaries forming, changing character, and becoming inactive as the configuration of plates changes through geological history. Subduction zones can cease activity when continental material clogs the subduction channel. Triple junctions where 3 plates meet migrate as the plates move, and new plate boundaries can form within previously coherent plates through processes that are still not fully understood. The initiation of new subduction zones has proven particularly difficult to explain, as the negative buoyancy that drives mature subduction is not present when subduction first begins, and significant force is required to bend a lithosphere downward and initiate the descent. Proposed mechanisms for subduction initiation include the collapse of passive margins under gravitational loading, the propagation of subduction from existing zones, and the development of new subduction at transform faults where lithosphere of different ages and therefore different densities is juxtaposed. The history of plate motions over geological time has been reconstructed using multiple lines of evidence, including magnetic anomalies on the ocean floor, paleomagnetic data from continental rocks, the distribution of fossils and geological formations, and the ages and geometries of mountain belts and other features formed at plate boundaries. These reconstructions reveal that the current configuration of continents and oceans is merely one frame in a continuously changing pattern, with previous configurations differing dramatically from what exists today. The supercontinent Pangaea, which Wegener recognized as having existed in the late Paleozoic and early Mesozoic eras, has been documented in increasing detail through these reconstruction efforts. Its assembly from earlier continental fragments and its subsequent fragmentation into the continents we recognize today, now well constrained by multiple types of evidence. The reconstruction of Pangaea required recognizing that the Atlantic Ocean did not exist prior to about 180 million years ago, that India was attached to Africa before rifting away and drifting northward to collide with Asia, and that the present broad dispersal of continents represents a maximum in the cycle of supercontinent assembly and breakup. The concept of a supercontinent cycle has emerged from the recognition that Pangaea was not the only supercontinent in Earth history, but rather the most recent in a series of assemblages and fragmentations extending back into the Precambrian. The supercontinent Rodinia, which existed approximately 1 billion years ago, has been reconstructed from paleomagnetic and geological evidence, though the details of its configuration remain debated. Still earlier supercontinents, including Nuna or Columbia, existing approximately 1.8 billion years ago, and possibly even earlier assemblages, have been proposed based on increasingly fragmentary evidence. The cycle of supercontinent formation and breakup appears to operate on timescales of several hundred million years, driven by the thermal evolution of the mantle and its interaction with the insulating effects of overlying continental lithosphere. Supercontinents trap heat from the mantle beneath them, eventually leading to thermal uplift, rifting, and fragmentation, while the dispersed continental fragments allow heat to escape more efficiently, until mantle flow eventually drives them back together into a new assemblage. the effects of plate tectonics extend far beyond the geological phenomena that most directly reflect plate boundary processes, influencing climate, biological evolution, ocean chemistry, and the long-term habitability of the planet in ways that are still being explored. The configuration of continents affects ocean circulation patterns, which in turn influence climate through the transport of heat from equatorial to polar regions, and the opening or closing of seaways between ocean basins can produce dramatic climate transitions. The formation of the Antarctic circumpolar current, following the opening of passages between Antarctica and South America and between Antarctica and Australia, thermally isolated Antarctica and contributed to the development of its ice sheet. The closing of the Isthmus of Panama approximately 3 million years ago redirected Atlantic currents and may have contributed to the intensification of Northern Hemisphere glaciation. Mountain building through plate convergence affects climate through the weathering of silicate rocks, which consumes atmospheric carbon dioxide and provides a long-term negative feedback on global temperatures, and through the creation of orographic barriers that affect precipitation patterns and atmospheric circulation. The relationship between plate tectonics and biological evolution operates through multiple mechanisms, including the isolation and connection of populations through continental fragmentation and collision, the creation of new habitats and ecological opportunities through mountain building and volcanism, and the modification of climate and ocean chemistry that affects selection pressures and survival. The breakup of Gondwana isolated populations of organisms on the separating fragments, leading to the distinctive faunas and floras of South America, Africa, India, Australia, and Antarctica that puzzled naturalists before continental drift was understood. The collision of India with Asia created new montane habitats and may have contributed to the evolution of distinctive Himalayan biotas, while also affecting climate patterns across Asia through the creation of the monsoon system. Mass extinction events have been linked to large-scale volcanic episodes associated with plate tectonic processes, particularly the massive flood basalt provinces that formed during continental rifting events, and that may have affected climate and ocean chemistry sufficiently to trigger biological crises. The long-term carbon cycle, which regulates atmospheric carbon dioxide concentrations and therefore global climate over millions of years, is fundamentally controlled by plate tectonic processes through their effects on volcanism, weathering, and the burial of organic carbon. Volcanic activity at mid-ocean ridges, subduction zones, and hotspots releases carbon dioxide from the Earth's interior to the atmosphere and oceans, while the weathering of silicate rocks on land consumes carbon dioxide and transports the carbon to the oceans in dissolved form. The burial of organic carbon in sediments and the precipitation of carbonate minerals represent sinks that remove carbon from the surface system, and the subduction of these materials returns carbon to the mantle to complete the cycle. The balance between these sources and sinks determines atmospheric carbon dioxide levels and therefore climate, and changes in plate configurations, mountain building rates, and volcanic activity have driven long-term climate variations throughout Earth history. The unique features of Earth among the terrestrial planets appear to be intimately connected to the operation of plate tectonics, which among the rocky bodies of the inner solar system appears to be uniquely active on our planet. Mars and Venus lack the organized pattern of discrete plates and plate boundaries that characterizes Earth, instead displaying tectonic styles that involve either stagnant lid behavior, in which a single rigid shell overlies a convecting interior without participating in the convection, or episodic global resurfacing events, as proposed for Venus. The reasons for Earth's uniqueness in this regard remain debated, but likely involve the presence of water, both at the surface and incorporated into minerals in the interior, which reduces rock strength and facilitates the processes of plate boundary formation and subduction. The operation of plate tectonics on Earth has likely contributed to the long-term habitability of the planet by regulating climate through the carbon cycle, generating the magnetic field through core convection linked to mantle dynamics, and cycling nutrients and water between surface and interior reservoirs. The future evolution of plate configurations has been explored through projection of current plate motions into the future, suggesting that in approximately 250 million years, the continents may again be assembled into a supercontinent. Various reconstructions of this future supercontinent, given names including Pangaea Ultima, Nova Pangaea, and Amasia, differ in their details depending on assumptions about which plates will become dominant and which oceans will close, but they agree that the cycle of assembly and dispersal will continue as long as the mantle retains sufficient heat to drive convection. The Atlantic Ocean may continue to widen until its spreading ceases and subduction initiates along its margins, eventually consuming the Atlantic basin and bringing the Americas back into contact with Africa and Europe. Alternatively, the Pacific Ocean may continue to close as it has throughout the Mesozoic and Cenozoic, with the circum-Pacific subduction zones consuming oceanic lithosphere faster than the Atlantic, and Indian ridges can create new material. The development of plate tectonic theory has influenced not only how geologists understand the Earth, but how society approaches geological hazards, mineral and energy resources, and environmental challenges. The recognition that earthquakes, volcanic eruptions, and tsunamis are concentrated at plate boundaries has improved hazard assessment and risk management in vulnerable regions, though the prediction of individual events remains beyond current scientific capability. The understanding that mineral deposits and petroleum accumulations are controlled in part by plate tectonic settings has guided exploration efforts and increased the efficiency of resource discovery. The recognition that the carbon cycle operates over millions of years and is ultimately controlled by plate tectonic processes provides context for understanding the current perturbation of this cycle by human activities and the timescales over which natural processes can restore equilibrium. The study of plate tectonics has also influenced other scientific disciplines, providing a framework for understanding planetary evolution, the history of life, and the connections between Earth system components that had previously been studied in isolation. The integration of geology, geophysics, geochemistry, oceanography, and paleontology within the plate tectonic framework exemplifies the synthetic approach that characterizes modern Earth system science. The recognition that the solid Earth, the oceans, the atmosphere, and the biosphere interact through plate tectonic processes has fostered interdisciplinary research programs that cross traditional disciplinary boundaries and that approach the Earth as an integrated system rather than a collection of separate components. The technological advances that made plate tectonics discoverable in the first place have continued to refine understanding of how plates work, with satellite geodesy now providing direct measurement of plate motions at millimeter-level precision. The Global Positioning System and other satellite navigation constellations can be used to track the positions of stations on different plates over time, revealing the velocities at which plates move and confirming the rates inferred from magnetic anomalies and other indirect evidence. These measurements have also revealed that deformation is not confined to narrow plate boundaries, but extends into plate interiors, particularly in continental regions where distributed strain accommodates far-field plate boundary forces. The recognition of such distributed deformation complicates the simple model of rigid plates moving on a spherical surface, but represents a refinement rather than a rejection of the fundamental plate tectonic framework. Ocean drilling programs have provided direct samples of oceanic crust and the sediments overlying it, testing predictions of the plate tectonic model and revealing details of ocean floor formation and evolution that could not be obtained by remote observation. The deep-sea drilling project, which operated from 1968 to 1983, and its successors, the Ocean Drilling Program and the Integrated Ocean Drilling Program, have recovered cores from hundreds of sites in all the major ocean basins, documenting the age progression of the ocean floor away from spreading centers, the variations in sediment composition with latitude and time, and the processes occurring at plate boundaries and in plate interiors. The confirmation that ocean floor age increases systematically with distance from mid-ocean ridges provided definitive support for the seafloor spreading hypothesis and demonstrated that no ocean floor older than about 200 million years exists, as predicted by the model of continuous creation at ridges and destruction at trenches. Seismic tomography, which uses recordings of earthquake waves to image the interior of the Earth, much as medical CT scanning uses X-rays to image the human body, has revealed the three-dimensional structure of the mantle and the fate of subducted slabs as they descend into the interior. These images show subducted material extending in some cases to the core mantle boundary, thousands of kilometers below the surface, confirming that the plate tectonic system involves the entire mantle, rather than merely a shallow convective layer. The images also reveal complexity in mantle structure that suggests the convection system is more intricate than simple models had assumed, with possible layering, chemical heterogeneity, and interaction between different scales of circulation. The relationship between the surface expression of plate tectonics and deep mantle processes remains an active area of research, with debates continuing about the degree to which plate motions are driven from below by mantle convection versus controlled from above by the properties of the plates themselves. The recognition that plate tectonics has not operated uniformly throughout Earth history represents an important recent development in understanding the evolution of the plate system. The thermal evolution of the Earth, with higher heat production in the past due to the decay of radioactive isotopes and the residual heat of planetary formation, likely affected the style and vigour of mantle convection, and therefore the character of plate tectonic processes. Some researchers have proposed that plate tectonics in its modern form did not begin until the late Archean or early Proterozoic, approximately 2 to 3 billion years ago, with earlier tectonic styles differing substantially from those observed today. The evidence for or against plate tectonics in the early Earth is difficult to interpret, as the rocks that might preserve such evidence have been subjected to billions of years of subsequent deformation, metamorphism, and erosion. But this question bears directly on understanding how the plate system originated and how it may evolve in the future as the Earth continues to cool. The implications of plate tectonics for understanding planetary habitability extend beyond Earth to the consideration of what conditions might support life on other worlds. The absence of plate tectonics on Mars has been linked to the loss of its atmosphere and the cessation of its magnetic dynamo, conditions that make the Martian surface much less hospitable to life as we understand it than the surface of Earth. The possibility that plate tectonics or something analogous operates on icy satellites of the outer planets, such as Europa or Enceladus, has informed the search for potentially habitable environments in the outer solar system. The consideration of whether plate tectonics can occur on planets of very different sizes or compositions than Earth constrains the range of potentially habitable exoplanets and influences how astrobiologists prioritize targets for observation. The connection between plate tectonics and habitability represents one of the most profound implications of understanding how our own planet works, suggesting that the processes that shape the surface and regulate the climate of Earth may be essential to the existence of the biosphere that includes ourselves. The history of plate tectonic theory exemplifies patterns that occur repeatedly in the development of scientific knowledge, including the role of new technologies in enabling discoveries, the resistance of established frameworks to revolutionary ideas, and the eventual synthesis of diverse observations into unified theoretical frameworks. The rejection of Wegener's continental drift hypothesis by the geological establishment of his time reflected not merely stubbornness or prejudice, but the genuine difficulty of accepting claims that lacked adequate mechanistic explanation, even when the observational evidence was substantial. The eventual acceptance of plate tectonics required not only additional evidence, but evidence of a qualitatively different kind, evidence that addressed the mechanistic gap that had made continental drift implausible. The transformation from rejection to acceptance occurred rapidly once this gap had been bridged, demonstrating that scientific communities can revise even deeply held convictions when confronted with sufficiently compelling evidence and coherent explanatory frameworks. The ongoing refinement of plate tectonic understanding continues to exemplify the progressive nature of scientific knowledge, with each new observation and each new analytical technique providing opportunities to test, refine or revise existing models. The fundamental insight that the Earth's surface consists of the moving plates remains as valid today as when it was first clearly articulated in the late 1960s, but the details of how plates move, what drives their motion, how boundaries evolve, and how the plate system has changed over time continue to be investigated and debated. The persistence of open questions does not represent a failure of the theory, but rather the normal condition of any active scientific discipline, where the resolution of some questions reveals new questions and the acquisition of new data challenges existing interpretations while supporting the overall framework within which interpretation occurs. The educational challenge of conveying plate tectonic concepts to general audiences has informed the development of visualization techniques, museum exhibits, and documentary presentations that attempt to make accessible ideas that are inherently difficult to grasp because of the scales of time and space involved. The movement of continents at rates of centimetres per year seems almost static from a human perspective, yet over millions of years these slow movements produce dramatic reconfigurations of global geography. The challenge of conveying geological time, of making comprehensible processes that operate over millions and billions of years, represents one of the fundamental communication challenges in earth science education. The success of plate tectonic theory in becoming part of general scientific literacy despite these challenges reflects both the compelling nature of the evidence and the elegance of the explanatory framework, which unifies disparate observations into a coherent narrative of planetary evolution. The practical applications of plate tectonic understanding extend to issues of immediate societal concern, including earthquake hazard assessment, volcanic risk management, and the sustainable exploitation of mineral and energy resources. The recognition that large earthquakes occur at plate boundaries, and that the intervals between earthquakes represent the accumulation of strain that will eventually be released, has informed seismic hazard assessments in regions such as the Pacific Northwest of North America, where historical records are too short to capture the full range of earthquake magnitudes that can occur. The understanding of how volcanic arcs develop above subduction zones guides monitoring efforts and hazard assessments for volcanoes that threaten millions of people in countries surrounding the Pacific. The recognition that economic concentrations of many metals occur preferentially in certain plate tectonic settings, such as the porphyry copper deposits associated with subduction zone magmatism or the gold deposits associated with ancient greenstone belts, guides exploration strategies and influences investment decisions in the mining industry. The environmental implications of plate tectonic processes operate on timescales that far exceed human planning horizons, but nonetheless provide context for understanding current environmental challenges. The recognition that the carbon cycle operates over millions of years and is ultimately controlled by tectonic processes puts the current anthropogenic perturbation of atmospheric carbon dioxide into geological perspective, revealing that the current rate of carbon dioxide increase far exceeds anything in the recent geological record, and that natural processes cannot restore pre-industrial conditions on timescales relevant to human societies. This understanding does not itself dictate policy responses, but provides essential context for evaluating the magnitude and likely persistence of anthropogenic climate change. The geological perspective also reveals that the climate system has experienced much larger variations in the past than anything in recorded human history, suggesting that the apparent stability of recent millennia may not be representative of the range of conditions that can occur, and that future changes may exceed the bounds of historical experience. The intellectual journey from early speculation about continental mobility to the modern understanding of plate tectonics illustrates the cumulative and international character of scientific progress, with contributions from researchers in many countries building on each other's work across generations. The German origins of continental drift through Wegener, the British contributions to paleomagnetism through Runcorn and his colleagues, the American development of seafloor spreading through Hess and Dietz, the Anglo-American collaboration that produced the Vine-Matthews hypothesis, and the subsequent global community that has refined and extended plate tectonic understanding all demonstrate that major scientific advances typically result from collective efforts that transcend national boundaries and disciplinary divisions. The institutional support for ocean exploration, geophysical research, and basic science that enabled these discoveries reflect social investments in knowledge creation that have yielded returns far exceeding their costs in improved understanding of the planet and its hazards. The continuing evolution of plate tectonic science ensures that understanding of how the Earth works will continue to deepen, with new discoveries modifying and extending current knowledge in ways that cannot be fully anticipated. The development of new observational technologies, from satellite measurements to ocean floor observatories to increasingly sophisticated seismic networks, provides data streams that enable testing of theoretical predictions and discovery of previously unrecognized phenomena. The integration of computational modeling with observational constraints allows simulation of processes that cannot be directly observed, from the circulation of the mantle to the long-term evolution of plate configurations. The interdisciplinary connections between plate tectonics and other fields, from climate science to biology to planetary science, continue to reveal new implications of understanding how the solid Earth behaves and interacts with the other components of the Earth system. The story of plate tectonics thus represents not a completed chapter in the history of science, but an ongoing investigation into one of the most fundamental characteristics of our planet. The recognition that the ground beneath our feet is not fixed but moves, that continents have wandered across the face of the Earth throughout its history, that oceans have opened and closed and will continue to do so, fundamentally changed how humanity understands its planetary home. This understanding emerged through the patient accumulation of evidence, the development of technologies that revealed previously invisible features of the planet, the willingness of researchers to challenge established ideas when evidence warranted, and the eventual synthesis of observations from many disciplines into a coherent theoretical framework. The plate tectonic revolution exemplifies how science progresses and demonstrates that even our most fundamental assumptions about the world can be overturned when confronted with sufficiently compelling evidence, a lesson that extends far beyond the specific content of geological knowledge to the nature of scientific inquiry itself.